session of the day with Robin talking about operator operators.
Okay. Yeah, let's begin this tutorial. So the tutorial is quite undefined as to what it should actually be. So I thought about two things that we could do. There were actually more things that I prepared we couldn't get to, but I wanted to suggest two things. So one thing we could do is we look at this infinite tensor product construction that we had in the morning and do an exercise about that and see what other types of examples we can get out of that, so related to that. That's one option, or the other option is to connect to Gemma's talk and see how to do entanglement entropy for general von Neumann algebras. So there's also an exercise related to that. It's a bit, probably a bit harder to get through that, but it's up to you. So any preferences?
First one. Second one.
Both.
Both?
Yeah, both is also.
No, I can't do both. Maybe I can't even do one of them if the clock keeps running. So which one should we do?
Just ask for a show of hands.
Show of hand, yeah. So who wants to do the infinite tensor product stuff? 1, 2, 3, 4, 5, 6, 7. Who wants to do the entropy, entanglement entropy things? 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's the majority. Then we do this one. But I can talk about the infinite tensor product separately. Is that okay?
Yeah.
Yeah. Adam, you are the overall chair of. Okay. So then, what do we do? So in Gemma's talk, there was a bipartite system. So essentially, you had we had system A and system B, and in this case, it was like matrix algebra and another matrix algebra here. Well, CD, tensor CD, and you've got the matrices acting on this one and on this one. Okay, so we have a 2D-dimensional quantum systems. And suppose this overall system. So let me do this a bit. Okay. So we have this bipartite system, and we have given a pure state on the, say this is on my overall Hilbert space, so a pure state on here, which is then represented by a vector in CD tensor CD. That is what we have here. And it also corresponds to a density matrix, which you wrote down like that. Okay? So either of these two ways are fine. And then out of that, we show that we can take we can define, say, rho A as the partial trace. So let's call this system A. This system we call B. So we take the partial trace with respect to the second one of this rho, and we get rho A, and vice versa. We get the partial trace with respect to the first one, and we get rho B. Okay, and these ones, rho A and rho B, are in general mixed states. Here we start with something pure on the whole thing, and here we have something mixed. Now if we apply this GNS construction to these mixed states, we go back to something pure. Well, exactly rho here. Okay? that would be so the opposite direction of taking the GNS construction. So, and then the entanglement entropy of psi essentially, of psi was then defined as the von Neumann entropy of the state, or equivalently of the state. So this is just the von Neumann entropy of this mixed state. Okay, so the von Neumann entropy of a pure state, we saw today, that's always 0. So the von Neumann entropy of this one would be 0, but the von Neumann entropy of these two is not 0, and that's a measure for the amount of entanglement you have between A and part B. So that's what we saw today. And now there is a nice characterization of, equivalent formulation. So let's say proposition, but I'm not going to show this. So I'm going to show, say, let me write this down. So we can determine the entanglement entropy as the so-called relative entropy between two states, psi and phi, where phi is separable. So we saw what separable means. You can write it down as a sum of tensor products of states, and that's what is meant by separable. Okay, so here all of this psi is a pure state on this, let's call it a tensor B in a slightly sloppy notation, but in this bipartite system. And so these were finite dimensionals. Okay, so now we need to actually define this thing. Given two states, let's call them.
What is this?
I'm going to define it now. So giving two states, let's call them rho and sigma. So given two states, so these are density matrices. I'm never sure, should I use density matrices or the mathematical states? So these are density matrices. So given two such density matrices on your system, which in this case could be the bipartite system, but this definition doesn't require bipartiteness, then the relative entropy is defined as trace rho log rho minus log sigma. Okay, so this is the relative entropy between rho and sigma. Okay, so that's
those dimensions can be different, right?
for which ones?
A tensor B, CD or
Uh,
A tensor B. The system dimensions can be different.
yes, dimensions could, yeah, dimensions can be different. Yeah, you can still get the same formula for rho A and rho B. Yeah.
Should there
But-
be a minus sign in front of the trace? Or?
In front of which trace? Here?
Yeah.
No, there's no minus sign. There's a minus sign over there, but there's no minus sign here. So this should be the relative entropy. Okay. So one can actually, that means one can use this relative entropy as a kind of distance measure between the two states, and in particular in this case, use as distance measure between separable states and this non-separable entangled state. Okay? So that is fine for finite dimensions, and this formula works if you work with states on matrices, and actually also with states on B of H. So for type 1 factors, this is like a well-defined notion, and one can then define it like that. So that extends. Okay, so that is a statement, and so one can now define.
Robin, can I ask should I worry about what log of 0 is?
Log of 0. Yes. Yeah.
But I'm not
That's- Yeah, that's why I would prefer to have faithful states.
Okay.
Yeah. So here we can now use this as a definition actually. So the entanglement entropy of psi of like the state rho is defined as S E of rho, where we take the infimum S rho sigma and sigma separable. Okay, so that gives us a generalization of the definition that we have here. To mixed states, but still on like finite or on type 1 for Neumann algebras. Okay, so now we want to use this in order to work out something for more general for Neumann algebras. So the question is, how can I make sense of this thing for general for Neumann algebras?
Sorry, I have a question. Now you say, oh, it's infimum or sigma sigma. But rho now is your reduced state, if I read correctly.
No. I want the entanglement entropy of rho. Okay, rho can now be a mix.
So you
Here
think of rho as pure.
could be, but it could also be non-pure. Could also be mixed state. So in this definition over there, it has to be a mix. It has to be a pure state. But in this case, so this definition also works by putting mixed states in here. So I can now also use entanglement entropy for mixed states.
And in the same thing, will you need, like, can you say that it's achieved, would be achieved at a product state or not necessarily?
Yeah, so
sigma. I'm asking about sigma.
Whether it is actually achieved on a specific sigma.
I guess attainability is one question, but also could I just, so if sigma is pure, then being separable that would be equivalent to being a product set.
Sigma is pure?
If sigma is pure, then sigma being separable is equivalent to sigma being a product set. And I'm asking, would this definition change if I restrict it to pure sigma?
To pure sigma.
Or another definition than the proposition.
Yeah, I think you can't assume in general that it is pure. So even if we look at, so if rho is not pure, for example, if rho is of this type, then it is like separable, but it is not pure. And now you want this to achieve, so the entanglement entropy of this thing should be 0, because there's no entanglement in there. But if you want this to be achieved by using sigma just pure states, then I don't think you can get that. So you need to allow more general things. If you want to allow for rho non-pure.
But okay, in the proposition up there, your psi is pure.
Yes, so this proposition tells us is there in order to show that the original definition of the entanglement entropy is the same as this one when psi is pure. Now, this one here, I can now generalize to the case where psi is non-pure but mixed. While here, up there, I can't use mixed state.
Sure, but I guess I'm asking, in the proposition up there where psi is pure, does it still hold true that I can't restrict to pure phi?
Whether this one
Maybe
can be made pure.
phi is separable. You can say phi is the product state.
Yeah, that's what I'm asking.
Whether you can achieve phi as a product state.
So it is because that psi is the both states. So basically, this definition has it's like you have a Hilbert space, and you are given a state psi, and you want to measure its entanglement. So you're trying to find the nearest pure state, and then compute your distance from that pure state. That's the measure of entanglement. So phi is the nearest pure state, product state that is unentangled. So your measure of entangle of psi is the distance from the nearest unentangled state.
Yeah, and you
So
say that.
phi should be the product state. If we are talking about the density matrix, then sigma is the nearest separable state.
Okay. I have to work it out with more time.
We gave you an exercise.
That's not the right way. So I'm giving you an exercise now. And generalize this to general von Neumann algebras. So how can we do this? Because what we have here are mixed states, or mathematically speaking, density matrices, and they correspond to the states, normal states on type 1 von Neumann algebras. So for other types of von Neumann algebras, like this infinite tensor product that we saw today, that's not type 1, that was shown to be type 2-1, and we don't have density matrices there. Well, you have, but not every state can be constructed using density matrices. So there are states which are of different type. You can't just construct them as like a trace with a density matrix in there. So what can we do in this case? Yes.
But that relative entropy is not symmetric.
It's not. No, it's not symmetric. No, it needs to be a positive definite, and that works. So as properties of the okay. So the idea, in order to do this, is the following. So that was found by Araki, and no, the relative entropy of states, let's call them phi and psi, and they are not pure now, they are general states of M, definition. Is defined as, so we have phi, relative entropy S, phi psi, defined as phi. We have the logarithm, and here we have a strange operator, delta phi psi, that we're going to construct now. Okay? So one can write it down in this way.
This M is now of type 1. More general.
More general, yes. So this works for type 1 as well, if we have time. But we have time. Then we can work it out for type 1, but maybe we don't have enough time. So this is the general definition that would work for any type, for Neumann algebras, for any states. Okay, so we need to understand this delta phi psi. Okay, so the construction of this is now as follows. So I want these states to be faithful and normal. As in the morning. And then one can do the following. So remember the GNS construction for faithful and normal states. So let psi phi and psi psi be the GNS vectors. So in the GNS triple we had this Hilbert space representation and a vector at the end that we used as the purification vector, by the way. So we spoke about purification also in the quantum information lecture. So we have this vector state that we get out of, we start with a mixed state and we purify that and get a vector state out of that. And that was exactly this psi phi in the GNS construction. So these are the GNS vectors. I said they are cyclic and separating. So cyclic means if I multiply this by the von Neumann algebra, I get the total GNS Hilbert space. And separating means if I apply this to any vector, any operator, I get something zero only if that operator is zero. So these are two properties. And so they're cyclic and separating for my von Neumann algebra M and the commutant of M. For both of them at the same time. So that's why this is a very nice construction, a very nice vector. And it does something nice to both of them. And so now I define the following operator.
They are on different Hilbert spaces.
Yes, but we can identify it as so. Yeah. First of all, yeah. For the first part, they are actually in the same Hilbert space for this vector I want to construct. So x psi phi should be mapped to x star psi phi. So where is this one live? This one lives in M psi phi. Okay? And so this is a dense subspace of the Hilbert space. Okay, this is dense in here because this was assumed to be sigma. This is in here, and this one is again in an element in here. Is there a problem with this? All right? Okay. So, this is an operator. And yeah, this operator, so I'm defining it only on these vectors, not on the whole Hilbert space. I can show this something called an unbounded operator. We can use this as a core and extend that. And yeah, and I call the closure, I call S. Okay. And I can do similar construction for M prime and this gives me a closure. It's called F. And one can show that F star equals S and S star equals F. Okay, we have a Hilbert space here, so we can talk about the adjoint of an operator, and so this is the adjoint. So
This is worth mentioning. These are not linear.
These are antilinear operators. So antilinear means if you have like a complex scalar in there, pull out a complex scalar, you have to complex conjugate. Be careful about that. But if I compose F and S, two antilinears, I get back a linear. And that's what we want to do now. We define this operator. So, by the way, this F and this S, they depend on the choice of phi as such. Okay? I define this one as the composition of F and S, so in other words, S star of S. And I define this one as this way. Okay, so this is a positive operator, linear, and this is antilinear. In such a way that if you take the square, you get identity. Okay, so yeah, this is like not easy at all, and I just want to do this very quickly. J, yes, J is bounded. This is in general unbounded, at least if we are in infinite dimensions. So now we wanted to make sense of this one here. So in order to get this one here, we have to slightly modify. So we've already got the delta phi. There's only this little psi missing. So in order to allow us to write a psi here, we have to modify this construction a little bit. How can we modify it? We've already had two states here, so we could change something a little bit. Namely, we could keep phi here, but put psi here. So we start with x psi phi, and we map that to x star psi psi. Okay? So we change sort of the Hilbert space, or if we want to identify the two Hilbert spaces, they are isomorphic, then we could forget about that, but here we would have a map from x psi phi to x star psi phi. And then we get a new, so this gives us a new S, and it will also give us a new F. We do the same thing for F, and this gives us a new delta phi. Okay? So define delta phi psi as S phi psi star S phi. So maybe let's call this here S phi to emphasize that it all depends on phi. Okay, and so this is now again a positive operator, and hence we can apply functional calculus and compute the logarithm of this positive operator.
I'm sorry, I didn't get the definition. S phi psi.
S phi psi. S phi psi you would obtain by replacing this with psi. Okay? For x psi phi, you map that to x star psi psi.
But that will be a psi. So how is it dependent on phi?
No, here we have phi and here we have psi. Oh, sorry, shall I write it down? Okay, so S phi psi we define as the closure of this map. X star psi psi. And this is called, so we should use some names because maybe you see them again. These are quite famous operators. So I just want to introduce the name. So this is called the modular operator of M phi, and this is called the modular conjugation of M phi, and this is then called the relative modular operator. Okay, this is the relative. So not this one. This one. This is called the relative modular operator, and they have some very nice properties actually. So if I take my von Neumann algebra and I sandwich this between the modular conjugation from the left and to the right, I get something new. Namely, I get exactly the commutant of the original von Neumann algebra. So if I want to compute the commutant of von Neumann algebra, I can obtain it by sandwiching between two copies of J phi and get that out of that. And yeah, some very nice and complicated deep properties that we're not going to look into. Just wanted to define this. So with this definition, this one here, then makes sense.
The relative modular is not going to be an element of my form.
Pardon? No, these modular operators, they are not an element of the von Neumann algebras. They are
Applied state. So your definition of the relative entropy is applied state phi to the log.
Yes. Yes. So yeah, in the GNS construction again. Okay, so this is like a maybe complicated definition, but we can work that out in our starting situation, in the initial situation of finite dimensional algebras again. So we see what this actually means in finite dimensions. So we already saw in the morning how to do the GNS construction for finite dimensions, and we get exactly the purification from Gemma's talk out of that. And so this can also be done in finite dimensions. Example. So let's do things in finite dimension. So what do we want to do? We want to compute this one here in finite dimension. So let this be like MD, and we have two states. Well, let's call them phi and psi, but they are faithful states, so they correspond to density matrices, which have non-zero entries on the whole diagonal. Okay, so that is what we have here. So can we now compute this? So I wanted this to be an exercise, so maybe I should give you like 2 minutes and think about how to compute this, the operator S. So compute S, maybe S phi, and then delta phi, J phi, and also the relative ones. Okay, so I give you, let me take a piece of paper, give you 2 minutes. I think it can't be solved in 2 minutes, but at least we can start thinking about it, and then we want to work out together. So the starting point is the GNS representation that we constructed in the morning for this state. So maybe I can write that down again. Where can I write this down? Okay. Now in this version it's slightly different. So the map that we have here maps x to x times rho 1. Okay. And the inner product that we have then be So maybe we should try and gather some results. I see people are very keen on carrying out the computations. That's nice to see. Maybe the first step we'll do together. Maybe I'll give you some more time after that. So what do we want to do first? The first thing we need is clearly this operator S, right? Because in order to define everything there, we need S, either the relative or the other one, the original operator. So how do we get S? What does S do? So the general vector in this GNS, purification Hilbert space, can be written down as a matrix times the square root of this density matrix. Okay, that is the way I chose my purification. So we saw this is not unique. Gemma mentioned that as well. You can choose different types of purification, but you can identify them via an isometry. So this is the one that we would like to use because it's good for comparing different states. So what do I get in this case? By definition, this gives me X star, and here we have rho. Okay? And yeah. So now we need to compute F phi of this. So the question is, how can we work with a commutant in prime? Because so far we represented the original von Neumann algebra on this Hilbert space, but now we need the commutant to act on this Hilbert space as well. So what operators commute with all the operators of my von Neumann algebra? That is the question. Has anybody got an idea? Right multiplication, yes, very good. So what is the commutant of MD in this case? So our algebra we start with is MD, and it acts not as in the standard way on CD, but it acts on MD. So our Hilbert space is where becomes C to the power of D squared. Okay, and so the commutant of MD is MD again in this representation. And so it must act in some way, and it acts actually by multiplication from the other side. So it acts by multiplication from the right on this cyclic separating vector. Okay, so if we write that down, what does F do? F phi of rho phi 1/2, and here we put some y that is out of the commutant, that is mapped to F phi of rho phi 1/2, and here we put y star. So we act. So we act from the other side. So if you look, you can use the same Hilbert space, just that the representation, so the original algebra acts by left multiplication on this cyclic vector, and the commutant of a commutant M prime acts by right multiplication on this cyclic vector. So it acts by multiplication to the right of this density matrix. The right of this density matrix.
So maybe afterwards you can explain. So as you said, right, this MD is asking more to CD, so CD.
Yes, so this Hilbert space, the purification Hilbert space is CD tends to CD, which is the same as MT.
Yes, so from kind of quantum info point of view.
From the quantum info point of view, you would take this space and you let your original von Neumann algebra MD act on this, and there you can easily see that the commutant is the one that acts on this component.
Yes,
so this is the commutant of this one. Okay? So that's nicer to see what the commutant actually is, but for this computation I prefer like the left and right multiplication version. Okay? So that would be, so this is the commutant of this one in H5. Okay? In H5. This is important that we are in H5. If we are just in the original Hilbert space, then MD has commutant, trivial commutant. We saw that MD is a factor, which means that MD intersecting with its commutant is just the complex numbers. But if we go to this bigger Hilbert space, then the commutant becomes big. So this is sort of what we have. And now F5 we have to apply to this vector. But it's not defined here. We need something like this. How can we turn this into something of this type in order to compute F5? Okay, thank you, Matt. So we have rho phi 1/2, rho phi minus 1/2. So that's where it's nice to be faithful. So all eigenvalues are non-zero. And now we can apply f phi to this. What do we get out of this? So this is now in MD, and this is of the type we got here. So what do we get out of this? This we just get, we have to take the star here, and we have rho phi 1/2 star of this, rho phi x. Okay, so we take the star of this part, and this gives us this part. Minus 1/2. And now we want to bring it back into this form. So what can we do, Matt?
Apply by another fraction.
Yes. So you can write this as rho phi x rho phi to the power 1/2, and here rho phi to the power minus 1. Okay? Just have to add up all the powers, and it makes sense. And so this is now the same one that we started with. And this is, by definition, the modular operator. So how can we write down the modular operator now in a nice way? So it's already here. Multiplication from the left by rho phi, multiplication from the right by rho phi minus 1. Okay? So that is the modular operator acting on this matrix algebra. So now we haven't got the time to compute the relative one, but one can do something similar. Who wants to guess what the relative one looks like? If I give you a minute, we need to wrap up. Okay. Yeah. Shall I complete this, or shall we end it here and leave it as an open problem? So the relative operator in this case be this one. Okay? And now if you take the logarithm of this, you can easily see that it is the logarithm of this minus the logarithm of this. And so this is essentially the logarithm of one state minus the logarithm of the other one. Okay? And so yeah, we managed to show this for like finite dimensional algebras. Okay, thank you for your help.